So hello everyone, welcome to week 6 of the tutorial sessions. So this time the topics that were covered were autoencoders and how to make these autoencoders more robust, or how to regularize these autoencoders. So the plan for today will be to cover the concepts that have been covered in class, uh, especially if you have any doubts regarding this, or if you have any other doubts for the last few weeks that have been covered. So if you have any doubts before that, you can unmute yourself and ask, or type it in the chat. And then also you can let me know what topics you'd like to be covered. Anything else other than, which part did you not, do you have doubts regarding these autoencoders? So let me join it my iPad. So today is week 6. So again, any doubts regarding the last few weeks, say PCA or SVD that was covered, orthogonality? Okay. So because this idea of autoencoders, it borrows directly from the idea of PCA, right? So some more people are joining. So let me wait. Let me start after some people have joined. So before that, yeah, we can discuss any doubts you have with your assignments, you have with your understanding of any topics. Okay, so let us start. So last week we covered PCA, right? So you know what is the usefulness of PCA. So basically, your need for PCA is because nowadays the data are too high dimensional, right? So if you click an image, there are a lot of pixels in the image, and if you're talking about deep learning, so each of these pixels is treated as a feature. So if you have a very high definition image, say 1080p by 1080p, so you'll have millions or billions of pixels, and you don't want that many features, because not all features are important, right? Because to identify something, you only need to know a very small subset of features. So PCA is a way of under helping you to understand or helping you to select the most important features. So basically, when you talk of PCA, we try to capture the most important principal components. Most important principal components. So by important principal components, we mean that the components uh, which preserve variance along the most important directions. Right. So now coming to neural networks. So can this, so suppose I have some image, say not an image, suppose I have a data set, say X, and now I multiply it with some matrix, say P. So now I get, so suppose my X is your n cross D matrix, that is, there are D features for n inputs, and suppose P is your n cross K, where K is less than D, right? And now if I do say P transpose K, so what will be the size of P transpose K? Anyone? Anyone? What will be the, because you need to understand these dimensions, right? Because then you can make decisions whenever you are trying to design some algorithm or uh, design an architecture, say. So what will be the size of P cross P transpose K here? So your P is n cross K, sorry, not K, minus P transpose X. Yeah. So your P is your n cross K, and then you have X, which is n cross D. So P transpose X is, okay, so you just have to multiply this and you get K cross D matrix, right? So basically what does this say? That you have K rows here and you have D columns here, and for each column you are choosing a K dimensional embedding. So instead of D you have some K dimensional embedding. So earlier, if you have, say, some input data point is D dimensional, so instead of the D dimension you're just choosing a K dimensional embedding for this. So now I have this K cross D matrix. Say now I suppose I name it as, say, some S, say, right? And now if I do X S transpose, I get the N cross D and D cross K, N cross K matrix, right? So basically earlier if I had, say, 100 dimension features here, and now if K is, say, 10, so from 100, so from N cross 100 matrix I go to a N cross 50 matrix if K is 50, right? So now we don't need, that is, we don't need to store all the 100 features. We are choosing, or we are selecting only the 50 most important features. Now can I represent this operation of doing a P transpose X or XS transpose as a neural network? So let us see. So first of all, you have the input layer X, which is your D dimensional, right? So now your goal is to multiply. So to make things simple, let us say that P is not, say P is K by N matrix, or let rather I will say, yeah, that's a mistake. Wait. So from d-dimensional X, we have to go to a k-dimensional space, right? So and you're doing this operation by P. So you need P to be, because X is your n by d, you need this to be n by sorry, k by d, right? Or sorry, rather d by k, if I am to do this, d by k. Now because this is a, you can look at it as a neural network, right? So you have your input layer here, and you have your first hidden layer here, and this P represents a set of weights here, right? So basically whenever you are doing now if we do say X, which is n by d, and P, you suppose I do that, our hidden layer output H1 is X times P. So your X is n cross d and P is d cross k, so you get n cross k, right? So basically this operation, so you H1 is in n cross k, right? So this is a weight matrix for your inner layer. And now if I want to go back again, I want to go back to the d-dimensional space. So if you remember, whenever we are discussing about PCA, we talk about how well we are able to approximate the true matrix, right? So suppose X is your given matrix, and after PCA, suppose you get some X tilde or X tilde, which is some approximation to this. So then you want that X and X tilde should be approximately equal, because you are doing a PCA, you are removing the number of dimensions or number of features, but you also want that the matrix or the data that you are recreating using only this smaller set of features, those two are equal, right? So that means if I am looking at it from a neural network point of view, you have this input layer, right? And now you're taking this input to a smaller dimensional space, which is k dimensional space, and now again you want to reconstruct it, right? Say this is some matrix Q, so we are going from k to d, so this will again be k cross d. So here you will get some x hat, right? And x hat will be your basically your q times, so here you are doing xp, q times xp. So this is basically your n cross k, and this is k cross d, or rather let me write it like this, xp times q. So this is your n cross k, this is k cross d, and now you get a n cross d matrix. So now if you have a matrix here n cross d, and you have, now you get the n the matrix which is n cross d. And now what I want is that I want to select the most important principal components such that my reconstruction error, so this was the reconstruction error, right? So that my reconstruction error is small. So that means my x and x tilde are small, that are close. That is, if I want to compute this quantity is small, right? So now my input was, this x, my output is this x prime. So basically now again I want to satisfy this condition, right? So what we're doing here is this PCA was basically a matrix vector multiplication type of algorithm, and we show that if we don't use any non-linearities, we can uh, we can also express, or we can also demonstrate that this PCA can be written as a sort of a neural network, right? We're just doing some matrix vector multiplications in this case. Now, so suppose let us talk about this dimension k. So in the lectures there was a proof which shows that if you have a linear decoder, so this part is the encoding layer. Right? Encoding layer basically takes your data and transforms it and transports it to a different dimension space. So you have your data in say 100 dimensional space. So here we are encoding it into a smaller dimensional space, say k, and then this is a decoding layer. So decoding layer basically transports your data from this lower dimensional space to the original space. So original space was 100. We took it to a 50 dimensional space. And now again we are taking the data from the 50 dimensional space to the 100 dimensional space. So this is the decoding part, right? So here k, I'll refer to k as the encoding dimension. So suppose we are doing a linear encoder. Suppose this is our linear encoder, and I say that k is equal to d in this case. So that means k may be larger or smaller. So that is important. So we'll get to that. So suppose we have a d-dimensional input layer, and again we go to a k-dimensional encoding layer. So suppose d is equal to k, and we are using a linear encoder. So that means we are multiplying x by some matrix p in this case. Suppose these two are equal, and then again we are taking it back to the d-dimensional space by matrix multiplying with some q. So what could be an issue with this? Anyone? If k is equal to d, say k is equal to d or k is greater than d. So basically what we want to do is that we want this x and x tilde to be small, right? We want this loss, say x minus x tilde to be small, and in the ideal case we want to be 0. So if you are saying that if we are not using any non-linearity, and I transform this d-dimensional point to say another d-dimensional space, and again take it back to another d-dimensional space, so what is the best case that can happen, right? So ideally we want 0. Can we get a 0? I mean, can we get back the same matrix if we are using a linear matrix, a linear encoder here? Is the question clear? So this is a very easy case, right? We are taking x, we are taking it to some other dimension. So we are keeping the dimension to be same. It is in d, and this is also in d. And then when you reconstruct it, suppose our loss is 0. That is, we are getting the exact reconstruction. So what is a possible p or possible q in this case? Anyone? Is this clear? Not clear? So another example, suppose I give you a matrix A and I multiply it by something. Suppose I multiply it by some matrix say R, and I get back the same matrix A. What is R in this case? Now you can type it in the chat also if you even if it is wrong. So this is a very simple question, right? You have a matrix A, or rather, if we're not talking about matrices, you have some number, say 5, and I multiply it by something and I get back 5. What is this something? No, no, we get back 5, right? Right. So in terms of matrices, what will be R then? So this is the identity matrix, right? So suppose A is your something like 3 by 3. Your R is your identity matrix, that is 1 0 0 0 1 0 0 0 1, right? So if you multiply anything by the identity matrix, you get back the same matrix, right? So now using this, so can you say what might be a problem if we do this? You have some input layer here. You are keeping the encoding dimension to be the same, and then you have some output here, and you have that this x and x prime are closed, that is their loss is 0. These two are exactly equal. So what might be a possible value for q, or what might be a possible value for p? So this will be your identity matrix, right? And this will again be an identity matrix, right? So basically you are not doing anything, you are just saying that x, I am getting ix, and again I am getting, so px is just I, again you are doing ix, and again you are getting x, which is x prime, which is equal to x. So you're not learning anything, you're just memorizing the full data, right? Whatever x you have, you're memorizing it, because the everything is same, and then you get back the complete data. So the problem with memorizing like this is, suppose a new data comes, suppose a new point comes, and which is not present in this, then you won't be able to do anything, because you only memorize the data that you have seen, but you also have to take care of data that you have not seen, right? You cannot memorize every data set in the world, because there can be an infinite number of data in the world, so you cannot memorize everything. So keeping k is equal to d is not good, because if you're doing say linear, I'm not going into non-linearity yet, I'm talking about linear, k equal to d is not good, because you can just minimize the data and you get a 0 error and you're done. Now what happens if you have an input d here, and you have some k which is greater than d in this case, and then you get back d here? So what do you think, will there be a case where x minus x tilde equal to 0? Here k is greater than d, and you have some matrices say p, q, and can you have a situation in it's again you get back the same matrix? So let me show you. So suppose your X was 100 dimension, right? And so that means you have some 100 features here. And suppose K is say 1000, right? So what you can do is you can exactly, so you have this 100 here, you have this 1000 here, and you want to get back the 100 dimension version of this, right? So what you can do is you can exactly copy this thing here. So you can say that the first 100 dimensions are this image and the rest of them all are zeros, right? And then when you're reconstructing, you will get back this same matrix here. So you'll get back this same matrix here, right? Because you are just copying this image or copying your data point, and you are storing it in this 1000 dimensional data point by just storing the first 100 dimension. Yes, in the lectures they have shown. So we are still talking about linear encoders now, because we're not talking. We're just talking about matrix type of problems. We are not talking about the sigmoid or non-linearities yet. So then the case will be different. So in this case, yeah. So whenever you're talking about linear means you're just doing matrix vector multiplication. We're not doing any sigma or 10 each on top of that, right? Hmm. AR is always, so this hidden dimension. So actually it depends, but whenever, so as I said, so this is for this is only for linear operations. This is only for linear when you're just doing, not always. So it will depend, right? When you go to non-linearity, this may not be the case, because in non-linearity you cannot have an operation which is same as the identity matrix, right? So I'm saying this is the case when you are just multiplying with matrices and you are not doing any sigmoid or 10h anyway, any of that non-linearity thing. Yeah, so again, if k is greater than d, you will have faced the same issues. That you will memorize the data set exactly and you will get a zero error, zero reconstruction error, but still will not be able to uh, learn the most important features that we have. So that is why what we do is we say that k is less than d, because if you have say 100 dimensions and the hidden dimension is say only 20, so in this 20 dimension you will only learn the most important most important features, right? You don't want to store these you don't want to memorize this 100 dimension or 100 features into this. You cannot do that. You cannot store it in 20 dimension. So you'll only capture most of these important dimensions. And now, so here we'll have your 100 dimensional input. We have some 20 dimensional input here, and then you'll get back this. So now we'll get some x prime, x minus x prime, which is not equal to 0, because now there is a loss of information. So because there is, you're only uh, you're only storing the most important 20 most important features, or some 20 features which capture the most information. There is still a loss of information, right? Because there may be some principal components that are not zero, so those things are not captured. So you'll not get back the exact x, you'll get back some approximation of x, so you'll have a loss that is non-zero. So these are only when we're talking, when we are in the linear regime, right? So that means we are only doing a matrix multiplication type of thing. So for neural networks are better. Why? Because we have these non-linearities, right? Sigma. So talking about this, so we have this d-dimensional input. We have some, so for convenience, let us say we have k, which is greater than d, and then Again, we'll have some t here, which is x prime, and you get back some x prime, right? So when you're talking about conventional neural network training, what do you do? So for conventional neural network training, what do? You have some x, you pass it through some hidden layers, right? And then you go to the output layer and give some output. Then you compare it with the true label or true score, and then you compute the loss, right? And then you back propagate the loss. So this goes to your output, this goes to your hidden layer, and you update the weights, and then this process continues until you are satisfied. So now in this case, our input is x. So how can you tell the network that we want to learn a uh, good representation of the input in some k-dimensional space? So we have to give some feedback, right? So how will the network know that I want to learn good, uh, say, k-dimensional representation of this input data x? So how do you get this feedback? We get this feedback by comparing our output with the input, right? So you want to compare this and this. So now again, we're changing this d-dimensional input to some k-dimensional space. So this part is the encoder. And again, because once we have the k-dimensional space, once we're in the k-dimensional space, we want to go back to the original dimensional space because that was where our original data resides. So this decoder will again take us back to the original dimensional space. So if you look at some books, they will show some diagrams like this. So this is your encoder, and you have some hidden latent space here, and then you have some decoder, right? And now you want to, so neural network requires feedback from you. It requires feedback from the output layer to update its weights. So how will they update its weights? Update its weight, the loss, right? So the loss is your basically your what is the quality of your approximation. So basically you want to say how much, if x prime is close to x or not. So based on that loss, so if your updates, if the reconstruction that you are getting is very bad, that means your x minus x prime is very large. So that means your weights need to be updated by a large amount, right? So if you're doing gradient descent, you will need to make large steps in the direction of the negative gradient. And then that information will be given by the loss that you compute here, and then you back propagate through the different hidden layers, and then you update the weights, and you do it as you would train a normal neural network. So so basically the forward propagation involves given an x, you pass to the encoder to get some latent representation. So this hidden representation is also called as latent representation. Then you pass through the decoder and you get back the reconstruction. And based on the loss between the input and the reconstruction, you update your weights. So once you update your weights, this latent representation will also be updated. So when you are at some minimum, say your x and x tilde are good enough, the representation that you learn will be the best representation of that data that you have learned. So that is basically the importance, or you can say how this encoder decoder thing works. So why is it useful again? So in the lectures, I think yeah, they showed you these images, right? This MNIST. So there is this data set M called MNIST. So those are basically images which contain some numbers. Say one image will contain some this So again, for us, it is easy to see like this is 1, this is 3, this is 3, this is 5, 5, this is 7, right? But for a neural network, it cannot directly distinguish, because if it says that this is what tree looks like, and then someone gives them a different type of tree, it will get confused, right? Because those are two different images. So take the example of 5 here. This is, so if the network learns that this is a very good, this is how the 5 looks like, and suppose during testing you give them an input something like this, it will not be a good result, because it knows that the 5 will have one straight line here, one straight line here, and a curve here. But here the handwriting is different. So what the network wants to know, what we want the network to know is that all of these threes, all of these fives, this 7, this 1, this should be encoded in a similar space, right? So suppose I'm saying that you have this space of numbers, some space of numbers. So say I wanted all the ones. So 1 can be written as this, it can be written as this, this, this. So there can be, based on the people's handwriting, there can be a lot of variations in one, right? So the neural network wants, it will be easier for the network to separate between say 1 and 5 if say the ones lie on one side and the fives lie on another side, right? So if this is the case, then the neural network can directly say that, okay, let me draw a decision boundary here. Anything that lies on this side is a 1, anything that lies on this side is a 5, right? So but for that the neural network has to learn this space, right? So neural network will have to learn this space where all these ones are, when we are going, so this is the k dimensional space. So if this is the d space, this is the k dimensional space, and this is the d dimensional space. So this is your k dimensional space. So the network learns that in some k dimensional space, all the ones, all the images of ones are close together, all the images of fives are close together. So basically after that, if we just say that given this k dimensional space, I pass it through some, say I pass it through some classification. There is some classification algorithm that they have, that we have, maybe a neural network, maybe something else. And then the classification algorithm will basically try to say that where should I draw this decision boundary such that on one side there are ones and on the other side there are fives. So we use this hidden dimension that we have. This is also called a latent space. And then we pass it through this classification algorithm, and then it will say whether our input is a 1 or whether it is a 5. So this is how the, but this is how the autoencoders are helpful to learn a good representation of the input that you have. So any questions till now? You can unmute yourself and ask also. So by latent space, I mean that so I have some, so here I only drew one layer for encoding, right? There can be multiple layers here. So suppose I have a neural network. So this is my input neurons, and then you have some hidden layer 1, another hidden layer, another hidden layer. Then again you have the output layer. So something like this. The output layer is 3. Okay. So now this is your input, this is your output, and these are your hidden layers, right? So now once I pass this data, so here the data is three dimensional. Here it is 4, 3, 5, 3. So if I look at the data that I get after this point, if I cut this network, say at this point, and I look at these representations, then we're looking at this three-dimensional. So originally my points were in three dimensions. Now my points are in four dimensions, right? So we look at their how these points are spread out in this four-dimensional space. So that is one latent space. So instead of this, suppose I cut it here again. So now I will have a latent space after two layers. We have a three-dimensional space. Or if I cut it here, we have a five-dimensional space. So depending on where you, uh, after which transformation you want to look at your data, so that is, so basically your data is going from a three to a four-dimensional space. From four dimensions again, we are going to a three, then again we are going to five. So depending on where you want to see your data, do you want to see your data at this place, or do you want to see here or here? So that is the latent space, like your data is taken to that space, and then after you say, after you get this space, how will if you want to classify or do something on this data, on this latent space, you can do it on this hidden space that we have. So suppose I want to do it here, so maybe we will get here. So this is a three-dimensional space. This will be very different from this space, right? So is your question answered? Oh, okay, okay, no worries. Okay. So again, I think in the class there was a nice demonstration on what does the neural networks learn, right? So I think I discussed it in one of my previous tutorials also. So basically, you have this multiple layers, right? You have this input layer, you have some hidden layer here, you have another hidden layer, and then say you have another hidden layer, just saying, and then you have some output layer. So this is not an encoder or decoder. This is just a simple neural network. So what do they learn? So again, so suppose I give you an image of a cat, so something like this, right? So this is a cat, say. My drawing is not good, but assume that it is a cat. So what does the neural network learn? So various experiments have shown that the first layer will try to learn only very simple features. So this, if we look at, so suppose I have these neurons here, right? And I want to see what these neurons are learning. So it will learn very simple things. Say one neuron will learn that it has a line like this, and the neuron will learn that it has a line like this, and the neuron will learn some that it has a curve like this, and the neuron will learn it has a curve like this, and so on. So this is their first hidden layer. So now when I go to the second hidden layer is, how do I define the second hidden layer? It is basically a combination of these, right? So these, and so on. So this second hidden layer will try to, so this second hidden layer will try to learn combinations of these. So say this and this, you can, it says that this image has this shape. So using these curves, say this and this, it will say that it has this shape, and another will look at the nose and say that it has this shape. So this is the second hidden layer. Similarly, the third hidden layer will try. So you have these neurons in the third hidden layer, and they'll try to learn the combinations of this. So now it will learn that there are 2 years, uh, and that this is inside of this, and so on, right? And then if there is one more layer, it will try to say that these two are related like this and this, right? And then it will say that at the output layer, once we have learned all these features, at the output layer it will say that this is a cat, right? Now coming back to decoder, so this was our decoder, right? So if here, instead of this being an output layer, suppose I remove this and I say that this is a decoder, right? So this is so here we have this encoder part, and here we have this decoder part. So what will it try to do? You have the image of a cat here, and it will try to reconstruct this image, right? It will not be able to do it exactly, but it will try to reconstruct this image of a cat. So if I look about how this data will look like, so if I look at only the first layer, it will say that based on only these lines, our data is uh, so cat images are somewhere here based on only these features. Say monkey images will be somewhere here, or because cats and monkeys, if you see both of them as ears, right? A monkey will also look the same if we are looking at a high level. So cats will be here, monkeys will be here, so dogs will be here. That is not very clear, right? So now if I go to the second layer, from the second layer we see that the cat's ears are of this shape, the monkey ears will be of say different shape. So now the space will be somewhat it will be able to differentiate, right? Your cat will be here, your monkeys will be say here. And then if I go more and more, we'll finally, after some layers, you can definitely say that the cat images are here and monkey images are here. So it will try to learn this uh, representation in a different space. And now if the data is very well separated, so we already know that if data is well separated, you can easily learn a linear classifier here. So that is the relation between encoders, the latent space, and why you use different number of hidden layers. So is the intuition clear? Actually, there are papers which have actually implemented this and saw that this is what actually happens. First, it will learn these low-level features, then progressively it will try to learn the high-level features. Hmm. So how the weights for these features decided? So again, why do you need the weights? We need the weights because why do we need weights? So you have some input, you multiply it some weight, then apply non-linearity on top of that, and you get the first hidden layer, right? And then after this, you get uh, you multiply it with some different weights, apply non-linearity, you get the second hidden, right? And so on. So you need to learn these weights. How do you learn these weights, right? How do you learn these weights? So again, this is where your discussions on backpropagation, gradient descent, and the loss functions coming, right? So suppose initially I have these random sets of weights. I don't know what these weights are. I just say some random numbers, say 3, 4, 5, 6, 7, something like that. And based on that, so you have this input, you have these hidden layers, and then you have this output. And based on these random weights, we learned we give some output, and then yeah, so initially we don't want the weights to be zero. We just say that those are very randomly initialized weights. So basically what we do is you have some weight matrix, say 5 cross 10, like maybe, and then we say that each number is taken from a normal distribution. Each of these entries is taken from a normal distribution, and then because these weights will anyway be updated, right? So that's why we don't care how we initialize it, but it is not a good practice to initialize from zero, because initially if weights are zero here, if weights are zero, all of these things will be zero, right? So initially your output will be very bad, because you are saying that you are giving h1 as input and you are getting a zero as output, and you don't want that. So we, instead of zero, we initialize it randomly. Hmm. So we have this random weights here, and you get the output. So once you get the output, we compare it with the true labels, the truth, and you get back the loss, right? So once you get back the loss, what we do, we back propagate. So during back propagation, what we do is we can compute the gradient of this loss with respect to a different activation layers, different hidden layers, and so on. So this back propagation gives us the gradients that we have. So using these gradients, we can update, right? So we know the update rule of gradient descent, right? Minus eta times gradient at t. So this is how the weights are updated. So basically, using these random weights, you generate some output, which need not be a good output. It may be very bad output, but the important thing is you get some loss and you take feedback from this loss. How do you get this feedback? By doing this back propagation, and then once you get back the gradients, you apply this gradient descent update, and now your weights will start looking good. Like it will keep on giving you good answers or good outputs. Good outputs in the sense that loss will decrease. So this weight updation is clear, right? How gradient descent helps, how back propagation helps, gradient descent helps. So any question on the things we discussed so far? Okay, good. Yeah, any questions on the things we discussed so far? Great. So now coming back to the lectures. So again, we saw this problem, right? If we have some, so the thing with neural networks is, if you show it a lot of data, it memorizes everything. So suppose, uh, suppose you are preparing for an exam and you know that your questions are from a certain book, textbook, right? So one smart thing would be to memorize every answer in the question and every question in the book, right? So if you have 100 questions, you memorize everything. And if you know that your exam contains only questions from that book, so you will get a good score. You may be able to get 100 out of 100 because you're memorizing everything. But what happens uh, when you don't get questions from that book, right? Suppose you get some, suppose you're doing some calculation and the numbers don't come from that book, it comes from some other books, then you'll be in problem, right? Because you have only memorized your answer, but you have not actually learned how to do that problem, maybe, or how to solve the problem. So these neural networks also face the same issue. So I think we discussed this in a previous lecture. we discussed this problem of overfitting, right? So is there anyone, should I explain overfitting or not? Because, can you say? Okay, seems everyone understands overfitting. Okay, good. So what we want is that we don't want our network to memorize everything, right? So we have this autoencoder, we have this X, we have this A autoencoder, and then we have some, I don't know, some function we want to apply to say y, right? So what we want is that it should generalize well. So suppose I train it on this image. So suppose I say that the 5 looks like this. That there is a straight line here, there's a straight line here, and there is a curve like this. So this is suppose a training point, right? Training point. And during testing, suppose I give it something like this. So this is also 5, we know that. But suppose the neural network only saw this image. So what will it think? That there is a straight line here, there is a straight line here, and there is a curve here. Try to look for these features. And here it will not, right? So here it will look, say that there is something like this. So this was not seen here, right? So this is here, this is not seen here, and there is this type of shape here, which again the network has not seen before, because it is only trying to look for this and this. So then the network will give us some garbage. With some luck it will tell us that it is 5, but most probably it will give us some garbage output. Say it will say that this is 3 or something, because some 3 can look like this, right? Which is wrong. So why does this happen? Because if we don't use this, because if we give only these good images, it will try to assign weight. So it will say that this is a very high weight, this is a very high weight, and this is a very high weight. That is, these are the most important features that the image can have, right? So that means this weight. So suppose this is your feature 1, this is your feature 2, and this is your feature 3. So with respect to feature 1, we have some W1, which is with respect to feature 2, you have some W2, with respect to feature 3, you have some W3. And this will be very high value. So this is say 10,000, this is 4,000, this is 5,000, something like that. So now when this type of image comes at testing time, this type of image comes, what will it say is that since it said that this line is most important, it will not be able to find this, right? So because this is assigning a high weight to this straight line, but if there is some feature which is of this shape, it will not be able to recognize it. So what we want, that we want it, these weights are small. We don't want to say that the most important feature is only this. We just want to say that there is some feature which looks like a straight line, but not that it should be only this one, not something like this or like this, right? So that thing is taken care of by something called as a regularization. So what the regularization does is it says that the norm of this W. So suppose I create a vector, suppose I create a vector W which has this W1, W2, W3, right? We want that the two norm of this W matrix is small. So how do I add regularization? So when you are talking about training a neural network, what is it we are doing? We are minimizing over some weights W, when minimizing the loss function given by this W, right? So this is what we are trying to do, minimize this loss given some W. And now when we are adding this regularization term, we say that there is another term, say lambda times W2 square. So what it does is it will try to minimize this whole quantity. Earlier it was only trying to minimize this quantity, and now it will try to minimize this complete the sum of these two terms. So for that to happen, this should be small, right? And this should also be small, right? Now what is, let us write down this thing. What is norm of W, 2 norm of W to W square? So this is basically W1 square, W2 square, W3 square, right? And if you want these to be small, if you want this to be small, we want that each of these things should be small, right? Each of these W1, W2, W3 should be small. Only then will we be able to minimize this. So if you say that these things are small, so these are small, it cannot have these large values, right? It will only have some very small values, so 0.01, because we want this loss to be minimum. 0.1, 0.5, 0.03, and so on, right? So regularization helps by it prevents the neural network from memorizing these things. So if I give large weight, it means that the neural network is saying that this is the most important features. I will not look at anything else. I'll only look at only this image. But that may not be the case. We want that it should look at all different possible variations of features. So now the weights are small. It will not say that I only look for the straight point. It will try to look at other points like this shape or this shape. So as even a test point which the neural network has not seen during training, it will be good. It will try to predict it in a better way. So that is what regularization does. Any questions regarding this concept of regularization? Okay, so the question is, autoencoders have entropy loss as well as square error loss. Okay, so that is a good question. So when you're talking about losses in autoencoders, right? So we have this X here, we have this AE, and we have this X tilde C, right? So now before this, when we are talking about regression and classification, so what type of losses are we talking about in regression? During regression, do we take the square error loss or do we take the entropy loss? Yes, someone can type in their answer. Not what do you mean by decreasing? Yeah, loss should decrease. No, I'm asking what is the type of loss you use in regression. So you know regression. Yeah, right. We want to decrease loss, but what is the type of loss you want to take? So suppose my output is say 3.5, and my true label is say 5. So what type of loss will you use here? Will you use squared error loss, MSE loss, or cross entropy loss? What type of loss will you use here? Anyone? Yeah, right. We'll use MSE, right? So for our case, it will be the 3.5 minus 5 whole square. And then there is some half term here. And now if I have a loss, say, mm, suppose I'm talking about binary classification, we have one means we have an image of a cat, and the true label says that it is an image of a monkey, that is 0, cat or monkey. So what type of loss will I use here? Will I use cat, or will I use MSE, or will I use cross entropy? Yeah, we'll use cross entropy, right? Because we are saying that the probability or the score of this should be 1 and the score of this should be 0. So I will write log pi plus 0 times log 1 minus pi. Say pi is your probability of monkey. mm, Probability of cat, say. It is something like this. It is not correct actually, but those are this is your y hat, this is your y, and this is your loss. So now coming back to autoencoders. Suppose my image, not the image, my inputs are of this form 1 0 1 0 1, and my outputs are something. So what should be the loss function that should be used here? So if my input is of this form, so my x, ideally my x tilde should also look something like this, right? 1 0 1 1 0 1, something like this. So what should be the loss? Yeah, right. We just saw this, right? That if our input is say 0 1 classification type of, oh yeah, if your outputs are classification type of outputs, say you output 1 or 0, then use cross entropy loss. So even here, if your data features of your data are say 1 0 data, or 1 0, they have 1 0 values, you use cross some form of cross entropy loss such that this is minimized. So this will try to give you something like this maybe, right? And then you try to minimize this. And again, similarly, if you have some data like 3.5, 2.8, 3.9, so here what will you use? So you'll use MSC here, right? So depending on the type of data, if your data is a binary, your features have binary values, so 0 or 1, you'll use a cross entropy loss. Or if it has some real values, then you will use this MSC loss. Yes, squared error is MSE. So MSE is mean squared error basically. Mean because you're taking the average over all the data points. Okay, great. Hmm. So yeah, regularization. So this is clear, right? There is no doubt in why do you need regularization, so that there is no overfitting to the training data, and that uh, your norms of these weights are very small. You don't give a large importance to any of these features. Okay, so again, so another type of and regularization that was discussed in the class was this denoising autoencoders. Right? So basically, you are given this input layer, and now what we want to do is you say that with some probability, some of these features are made zero. So this and this. So then you have this encoder part, you have this hidden representation, this decoder, and then the reconstructed image x tilde. So why we want to do this? Because again, the problem with autoencoders is that it may memorize the data, and we don't want the autoencoder to memorize the data, right? So now if I say that some some points are zero, so let me say that um, our x is of this form, say 1.299, something like this. And after this noise, so this is some x noise. So my x noise is something like 1.23.900.12. So now this autoencoder, this layers here. So this autoencoder will try to, what is its aim? Tries to learn a representation of this. Right? But now you can see that it is not getting the input to the autoencoder is not this complete data. It is only getting some a part of this data, right? It is only looking at this part of the data, so it is not able to see these features at all. So why is it helpful? It is because it will not be able to memorize the data because it has not seen these inputs. It is not seen that this is 8.4, this is 9.8. It will not be able to memorize this data. So basically, if you are reading some textbook and some pages of those are torn out, so you'll not be able to read those pages. But still, whenever you are trying to minimize the loss, you are comparing the loss between x hat and x, right? Your loss is between x and x hat. So even though you're not able to look at the complete x, you still have to learn about this x so that this loss is minimized, right? To minimize this loss. So this autoencoder will not be able to look at these pixels or these features, and still it should try to minimize this loss. So how will it do? It will just try to learn the most important features based on the available features that it has, right? So now there will be very less chance of overfitting because it is not able to memorize the complete data, but still it is able to learn good representations. So once a test data comes, there will be a good chance that it will be able to recognize that test data as well. So that is the simple addition of noise to this denoising autoencoders. So any doubts here? Okay, fine. So another type of regularization that was described was the sparsity, right? Sparse autoencoder. So again, here we are setting all of these to 0. So sparse autoencoder is basically saying that each neuron, sorry, each neuron should be, on average, it should be small. So this is same as saying that we want, so here we said, right, each of these weights must be small. It should not be very large. So sparse autoencoder says that each neuron, so each neuron will receive some input, right? It will receive say x1, x2, and here we'll have some h of some w into x1, x2, say. We wanted this is small. So if we want this to be small or this almost zero, so it will only capture the most important features. It will not try to learn everything. It will not try to memorize everything, right? So that is basically saying that we don't want to preserve all the principal components. We just want to preserve the most important principal components, the most important directions of variance in the data. So that is what a sparse encoder does. And another one was this contractive and autoencoders. So those are basically saying that the Jacobian is basically the rate of change of loss or rate of change of the activation given some input, and they want this to be small, right? Because we don't want any input to have a huge impact on any of these activations. We want that these activations should learn all of these inputs almost equally in some sense. So the contractive A is try to make this quantity, which is called the Jacobian. It tries to make the Jacobian small in sense of in terms of something known as the Frobenius norm. So I guess these are the things that was covered in the this week's class. So if you have any doubts, you can ask, or if you have any doubts regarding the assignments, I'll not give the solutions, of course, but any other doubt, we can discuss those. Okay, so the Jacobian is basically, yeah, Jacobian is basically your, it says that, uh, so you have a neural network here, right? And you have some, yeah, output here. So Jacobian basically says what is the rate of change of some neuron. Say here we have some neuron here. What is the rate of change of this based on once you change x, right? So this is what the definition of derivative is, because we want to say how does changing the input change your output. So this is what the Jacobian does here, right? Uh, so if we say that some changing some data heavily influences the Jacobian, that means your network is memorizing this data, that giving this x, this will give us the highest h in this case. If this is small, it will give us a small h. So it learns that according to x, it changes this much and this much. But we don't want. But we doing this not on it. Uh, so this Jacobian, this contractive AES, this regularization is only used for this autoencoders. I'm not sure if these are used in any other networks which are also autoencode, which are not autoencoders. It may be there, but I am not aware of that. But for autoencoders, we want your network to be able to generalize to any type of input, not only the inputs that we have seen. So if the Jacobian is for very large for some set of input and very small for some set of input, it means that it is overfitting to that input, right? So if only on this input I will get this image, but if it gets an input which it has not seen before, it will not know whether the age, because age only depends on the input x. It is not generalized. So that is why we want the Jacobian to be small. And Frobenius norm is basically this one. So you have some matrix, say A1, A2, A3, A4, and you have another matrix, say B1, B2, B3, and B4. So if I am talking about the Frobenius norm here, so this is basically computing the element-wise subtraction and squaring. So A1 minus B1 square plus A2 minus B2 square plus A3 square plus minus B4 square. So when will this Frobenius norm be small? This will be small if this is small, this is small, this is small, this is small. So basically, Frobenius norm says that these two matrices should be close in terms of the elements that they have. So this is the definition of Frobenius norm basically. Is that clear? So identity function is basically your identity matrix. So if I multiply some matrix, say A, with the identity matrix, I get back the same thing. So like for numbers, if you have some 5, I multiply it by 1, we get 5. So similarly for matrices, we have some matrix A, I multiply it, so with the identity matrix I, we get back A. So if some function is here, some function, I pass the input as A and I get back the A as output. So then this is your identity function. Yes. So identity function is basically this thing, right? That means you're memorizing the data. Basically, given some input A, if I just say that there's an identity relation between the A and the and some A prime. So basically, whatever I am giving, you're getting back the same thing, right? If A prime is equal to A, you're getting back the same thing. You're memorizing the data, and you don't want it to memorize, because if we memorize, then it will not be able to learn new unseen data. So contractive AE is basically a sort of regularization, just like your sparse AE and just like your L2 regularization that we saw. So this was your L2 regularization. So they prevent memorizing the data. So here what we saw was that it does not allow the weights to be very high. So here the sparse encoders, what it does was it does not allow these neurons to be activated uh, for for a large number of inputs. It is only activated for a small number of inputs. So similarly, this contractive AE does not want that your um, autoencoder learns or memorizes your data. That means if it memorizes, it means that if you give A, it will give A. If you give B, it will give B. Right? So that means it is just learning an identity function. So ideally it wants that if you give A as input, it will learn something like A prime, which is not exactly A, but which is close to A. Similarly for B, it should give B prime, which is close to B, right? So here, because it is not exactly equal, this is not an identity function. This is an identity function, and we want this. This is a good case. This is a bad case. We want this because it helps in generalization. That is, on an unseen data, it will not give garbage answers. So is that clear why we don't want the A to learn identity functions? Good. Yeah, so if you have no further doubts, you can leave. I'll be available till 8 p.m. If you have any doubts, you can discuss it till then. Otherwise, you are free to leave.